In this lecture, I'm going to teach you how to generate simulated data using a Latinsquare design. So that's the kind of design that we use when we do experiments in real life. In the previous simulation lecture that I showed you, that I gave you, I didn't use a Latinsquare design just for pedagogical reasons, just to make it easier to explain the story. In that lecture, every subject was seeing every condition of every item. That's not a Latinsquare design. So let me remind you how a Latinsquare is set up. Right, so if you remember, the basic setup of a Latinsquare design is like this. So suppose I have 4 items in my experiment, just for illustration, and I have 4 conditions, so a 2 by 2 factorial design. In that situation, what I will do is I will design one item with 4 versions, right? And I will distribute them across 4 groups, and then I will create the next item also with 4 versions, but I will distribute the 4 versions differently. So the first set had A, B, C, D. The second set will be B, C, D, A. The third item will have C, D, A, B, and the fourth will be D, A, B, C. If I had a 5th item, I would again start with A, B, C, D, right? And then 6 and so on, right? It would go on like this. So the idea is that we rotate the conditions of all the items such that we have one condition from each item in each group. Okay, so every group has the property that it has one condition, one of the 4 conditions from each of the items. Okay, so this has the great this kind of design has the great property that it completely balances the presentation of the different items in different conditions, right? So I will see, for example, in group 1, I will never see item 1 more than once. I will never see item 2 more than once. I will only see each of these items in one condition, right? And the same holds for the other groups, right? So that's the Latinsquare design. So we're going to use this design for doing our experiment. And so let me get to my code here. So let's assume, just for illustration, okay? So let me say that I have 4 items, right? And let's assume that I have 8 subjects, okay? So let's say that's the situation. And so what this function that I have here, where is it? Right, so in this function that I'm going to write for generating simulated data, this gensim log normal 2 by 2 design, in this function I'm going to run the following commands. Okay, so I'm going to explain how I generate the Latinsquare here, okay, in this function. By the way, in this lecture I'm only going to focus on 2 by 2 repeated measures designs because I'm using this canonical example to explain the general principles. You can of course generalize this to any design that you might actually be working with. Okay, so let me focus first in this when I'm trying to explain this function on how to generate data, but let me first focus on this part of the function, okay, and tell you what it does. So let me first run this part of the code and show you what I get. If I run this code here, G1, what this code will do is that it will generate the group 1 column for me. So if you remember in this thing that I wrote here, this group 1 column consists of item 1 in condition A, item 2 in B, item 3 in C, and item 4 in D. That's what I've done here in this piece of code, okay? G2 will produce the second column. Right? So this contains BCDA. This third command here, G3, will produce CDAB, and the fourth one will produce DABC, right? So that's what these 4 things do, right? And then once I've produced these 4 groups, what I'm going to do is that I'm going to assemble a data frame for the number of subjects that I'm going to have, right? So imagine that I've got 8 subjects, right? Let's say I'm running an experiment with 8 subjects in this 4 group experiment. What I'm going to do is I'm going to assign 2 subjects to each of these groups. That's how I'm going to get 8 subjects. And what that means is that the 2 subjects that go to group 1 are going to deliver 8 data points to me, right? So they're going to deliver 1A, subject 1 will deliver 1A, 2B, 3D, 3C, 4D, and subject 2 will also deliver 1A, 2B, 3C, 4D, right? So that's what it means when I have 8 subjects. I'll get 2 subjects in each group, and each subject will produce 2 instances of this column here for me. Okay, so that's what I'm doing here. I'm generating that column for the number of subjects, the 8 subjects that I have. So look here. So what I get out of this command is that I get 2 repetitions of the Latinsquare part of group 1, right? So the ABCD is repeated twice. So this represents the first 4 rows represent the first subject, and the second 4 rows represent the second subject. I'm going to add the subject IDs in a moment. So I do the same thing for the other groups, right? And so I get all the groups data. So now I'm going to concatenate it using row bind. I'm going to concatenate all the 4 groups for the 8 subjects, and then I'm going to add a subject column. This subject column will now contain subject IDs going from 1 to 8, and subject was 8, and each of these numbers going from 1 to 8 will be repeated 4 times, right? So that's what I've shown you here. Here I'm going to repeat subject ID 1 4 times, then subject ID 2 4 times, and so on, right? So that's what I've got here. And so when I do that, I've got a simulated data frame that contains a subject ID as well. Okay, so now what this is good for is that I can now add the contrast codings, right, because I know the condition levels. And once I have the contrast coding set up as 3 more vectors, I'm ready to simulate data like we've done before. Okay, we're going to go row by row and produce a data point each time. Okay, so the next step I will do is I will define my contrast codings. So you have to be very careful here. Right now I'm assuming that the first factor's 2 levels are such that the first level is in the condition labels A and B, and the second level is in C and D. You have to make sure that that's true in your data, right? Don't just blindly use this code. The second factor level I'm assuming is such that A and C represents the first level and B and D the second level, right? And similarly the interaction is this one here. So I'm just calling these factors C1, C2, and C3 for convenience here right now. Okay. All right, so the next thing that I do, of course, is that because I need to have random effects for the 4 predictors, I'm going to have the intercept and the 2 main effects and the interaction. So there are 4 fixed effects. So if I fit a maximal model, I'm going to have 4 random effects, right? So I'm going to generate a multivariate normal distribution with 4 dimensions, right? So the variance covariance matrix for the subject's random effects will be a 4 by 4 matrix, a very complicated matrix now, right? The diagonals will contain the variances, and the off diagonals will contain the covariances, right, which contain the standard deviations, the correlation, sorry. Okay, so what I've done here is that I'm generating the subject random effects. Of course, in order to generate these subject random effects, I have to know how many subjects I have. So this I've calculated here. So I should get 8 subjects here, right? Because that's how I set up this simulation. This variance covariance matrix will have to be defined by me, and I'm just going to show you how to do that. Okay. So I've created my variance covariance matrix here, and I generate my random effects here for subjects and for items, same situation, right? And then I start generating my data row by row. Capital N is the number of rows in my SIMDAT data frame, right? And RT is the vector that will contain the simulated data. So I go from row 1 to row capital N, and each time I compute this long function here, right? So this is the log normal that I'm going to generate a random data point from. I'm going to generate one random data point with standard deviation sigma e, which will be a parameter that I give to the simulation code. And I will use exactly the same method that I have shown you earlier. I'm going to have my fixed effects, the beta 1, then the adjustment, intercept adjustment by subjects and by items will be computed as I had discussed earlier. So I will look up the U matrix. Remember what the U matrix is. The U matrix has as many rows as there are subjects and has 4 columns. Why 4 columns? Because there are 4 random effects. Okay, so I will look up the U matrix here, right? So what I'm doing here is I'm looking up the subject ID in the ith row of the SIMDAT data frame. So the subject ID in the first row will be subject 1. Okay, so I look up subject 1 and then look up the first column in the U matrix. That's the intercept adjustment by subjects, right? So I put that intercept adjustment here. Similarly, I put this intercept adjustment for items here, and then comes the first main effect factor, right? And then I take the second intercept, the second column of the U matrix that contains the adjustment to that slope, right? And I do the same thing with the items, right? That the second column of the W matrix will give me the slope adjustment by items, and then I'm multiplying by the first factor that appears in the ith row of the data frame, and so on, right? For the other factors, it's the same old story. Okay, so that produces the simulated data for me. I plug in that simulated data into my SIMDAT data frame, and then I just do some bookkeeping. I create subject and items as factors, and then I just print out the simulated data. That's the simulation code. It's pretty straightforward now, right? The only innovation here is that now we have first generated a Latinsquare data frame, and then we walk through that data frame in the usual way. Okay. All right. So the next part of this lecture is about obtaining the estimates that will go into this function, right? So if you remember the function is set up such that certain parameters have to go into this function in order to generate the simulated data. We need the beta vector, so a vector of 4 values for the intercept and the 3 slopes. We need the variance covariance matrix for the subjects and for the items, and we need the standard deviation of the residual. Okay, so my throat is drying up, so I'm going to pause the video and get something to drink. Okay, so how do we generate this? How do we estimate these parameters? So what we typically are going to do, or what I typically do rather, is that I generally use the parameter estimates from an existing data set. The reason I do that is that typically when I'm working on a research problem, I will run a series of very similar experiments again and again. And I've been doing this all my life. So for example, let me just pull up an example paper and show you this paper, for example, in 2010, right? So this paper, the research here was started in 2004 or something like that, or was it 2006 maybe? Yeah, so we ran 7 experiments in this paper, and they were very similar experiments, right? So once you run one experiment, you have some idea, or 2 experiments, you have some idea of what the estimates are going to look like for the variance components, for example, and for your fixed effects as well, right? So you can use these. If you're working on a problem over an extended period of time, you are going to run multiple experiments. So you can use the estimates from your initial experiments to decide on the parameter estimates for doing your simulations. Okay, so that's my motivation for using existing data. So as an example, what I'm going to do is I'm going to use existing data from somebody else's experiment. So this is Levy and Keller, because I'm going to run follow-up experiments, on this study. So their experiment was a 2x2 factorial design, and the details of the design don't matter. What matters is that there are two main effects and one interaction. Okay, so we load the data, and then I create a condition column, and once I've done that, I start defining my contrast coding. So it just turns out that the way this experiment was set up was that the first factor, which they call DAT for dative, right, had the levels AB for one. The first level was AB and the second level was CD. The second factor was called adjunct, right, ADJ, adj, and B and D constituted one of the levels of the factor. Okay, so you have to be careful about which levels represent which conditions represent which levels of a factor. Okay, and then the interaction was this thing here. Okay, so this is our contrast coding setup for the two main effects and interactions. The interaction is called int, right? And so what they did, this is their data analysis. They had removed the 0 millisecond data points. This is an eye tracking study, and we're looking at total reading times, and we're looking at a particular region in the sentence. So what they've done is they've removed the 0 millisecond reading times, and so they have this data frame which they're going to use for data analysis. So I'm using their data frame the way they did the analysis. I'm repeating it. So now what we do is we fit a linear mixed model to the total reading times on the log scale, right? And we look at the main effects and the interaction, and we fit a maximal model. There will be some singularity warning here, but we can ignore it for reasons you will see in a moment. Okay, so the model summary, the model output shows a strong effect of this dative factor here. So if you look at this t value, you can see that it's a very strong effect, right? So all the others are non-significant. So let's focus our attention on this particular main effect of the dative factor. Okay, this is what we're going to use. We're going to compute, do a power analysis for this factor. I want to stress here that when we do a power analysis now, we are doing a power analysis for a future study. We are not investigating the power properties of this particular data set. That kind of power analysis is called, when you examine the power properties of an existing data set, that is sometimes called post hoc power. And that quantity is a nonsensical quantity that you should never compute. The reason is discussed in this paper by Hoenig and Heise. It's a famous paper in statistics. They explain in that paper that once you know the p-value, you already know the power, the post hoc power. So computing it doesn't add any information once you know the p-value. So there is no point in computing post hoc power. What we are doing, however, is we are computing prospective power for a future experiment that we will run as a follow-up to this study. Okay? We are just using the estimates from this experiment to think about what would happen if we were to run the experiment again. Of course, in the new experiment, the standard deviations would be different, the variance components would be different, and everything would be different, right? Because they'd be different subjects. But if you want a starting point for doing a power analysis, we need to start somewhere, right? We have to make some commitment about the parameters that we will assume when we do the power analysis. So that's the purpose of this power analysis that I'm going to show you. It's a prospective power analysis. Okay. Alright, so the first thing we are going to do to plan ahead is to ask ourselves what is the plausible range of effect sizes. Okay, so we have to study this problem now and think about it. Now, remember, let me just pull up, remember the following thing that I had taught you long ago. Like if you're analyzing data on the log millisecond scale, and let's say you have two predictors, okay? Let's say I have two predictors. I've got this dative predictor which is coded plus 0.5 minus 0.5, okay? So I fit this model on the log millisecond scale. Now, what is the, if I want to know what is the mean reading time from the model on the millisecond scale, okay? What's the mean reading time on the millisecond scale for dative coded as plus 0.5? Okay, what's the mean reading time on the millisecond scale for the dative coded as minus 0.5, right? How would I compute that? Right, the way I would do that on the log scale is that I would replace this with 0.5, right? And here I would replace this with minus 0.5, right? That would give me the estimates on the log scale, right? How would I get to the millisecond scale? I would exponentiate both sides. Exponentiate this side and exponentiate this side. What that will do is that because the exponent is the inverse of the log, on the left hand side I get the reading time level. On the right hand side I get the predicted or the expected reading time. Okay. Similarly here I'm going to also get the expected reading time, except that this will be minus 0.5, right? Okay, so now if I want to know the difference between these two conditions, how would I compute that difference? I'm going to compute that difference by subtracting this condition value on the millisecond scale from this one here, right? So this is something I had shown you several lectures ago. So this is how I would compute the estimate on the millisecond scale for a difference between the two conditions, right? And so that's what I'm going to do next. So what I have here is I've extracted the intercept and the slope for the dative effect, and I've done this calculation that I just showed you, that I derived for you, to calculate the effect on the millisecond scale. So this is the difference between the two, so this is the dative effect basically, right? The main effect of dative is about 80 milliseconds, right? However, this effect has a standard error associated with it. If you look at the model output here, right? So this model output shows some standard error associated with it. That means this quantity minus 2 times 0.06 would give me the lower bound of this estimate. So let's compute that. The lower bound would be the slope minus 2 times the standard error of that slope. I just extracted that from the coefficients here. Okay, and the upper bound would be the slope plus 2 times the standard error of that slope, right? So the lower and upper bound are these quantities on the log millisecond scale, right? So I can now take this lower bound and this upper bound, and I can compute again using this same calculation the lower bound and the upper bound on the millisecond scale, and that quantity is a very broad range, right? The lower bound is 17 milliseconds, the upper bound is 141 milliseconds. That is a very broad range of possible values for this dative effect. Now, once you develop some experience in doing data analysis, you will realize that such a broad range implies that there is we have low statistical power, right? So we will just establish that in a moment. Okay, so basically what we can say is that we can take the mean estimate from the data set and the standard error from the data set and assume that our effect is somewhere, that our the effect of dative, right, is can be modeled or can be assumed to range from 15 plus minus 2 times 0.06, right? That's what I'm saying here, right? So what I'm really doing here is strictly not a frequentist way of thinking, because for frequentists, the true effect is going to be a point value. It doesn't have a distribution associated with it. Right now I'm acting like a little bit like a Bayesian, right? Because Bayesians can have uncertainty about the effect, and they can describe it as a probability distribution, and that's what I'm doing here, right? So I'm acting like a Bayesian here. But the practical consequence of doing this is that I'm going to treat the 95% confidence interval here. Okay, remember this lower and upper bound here, 0.03 and 0.27. I'm going to use these lower and upper bounds as a marker of my uncertainty of this estimate. This is a slight abuse of the confidence interval approach, but I think it's good enough. It's close enough to the Bayesian estimates that I can actually do this and think about my uncertainty of these parameters and put that in the power analysis. So I will show you now how I do that. Okay. So once I have fit the model, I'm going to extract all the parameter estimates. So how do I do that? Let me show you. I'm going to just use the summary and the coefficients function which you've seen before to extract all the beta parameters. So the first column, what I'm doing here is that I'm just extracting this first column, the 4 numbers here, right? So that's what I've done here. For the betas, I have a vector of 4 values here. I've extracted the sigma, the standard deviation, using this command. Then I've extracted all the standard deviations of the random effects. Okay, so let me explain what's going on here. So let me just fit this model. Where's the data? Here's the Levy and Keller data. So let me set it up, and once I've set it up, I'm going to fit this maximal model and show you what I get. It takes a few seconds to fit this model. And so if I look at this model, what happens here is that I've got a vector of standard deviations here, vector of 4 standard deviations, and a vector of 4 standard deviations here, right? So this is for subjects and this is for items, right? And there are the correlations here that will go into the off diagonals in the variance covariance matrix. Okay. All right. So these are the subject random effects, the subject standard deviations, and then these are the subject correlations. Okay, so all these correlations I've also extracted here, right? And what I then did was I just because I'm getting a singularity warning here. If you look here, there's a singularity warning coming here, and that's probably coming because these correlations are such. This value is very high, and it could be causing making this variance covariance matrix non-invertible. I'm not sure exactly what the reason is that it's singular, but I'm going to make the variance covariance matrix more regular by changing all these correlations to 0.5. Here also I will change all these correlations to 0.5 just for convenience. Okay, so just so that I can simulate the data. You can play with different values if you like to see what happens there. So let me see, where was I? Let me extract the values in front of you right now. Here we go, right? So I'm now extracting all the estimates. So this is the interesting thing I was talking about. I've extracted all the standard deviations. These are the 4 standard deviations that you saw in the model output, right? So it's 0.38, 0.12, 0.08, 0.12, and if you look at the output here, 0.38, 0.12, 0.08, 0.12, right? So this is the 4 numbers here, and these are the correlations. The next line is the correlations, right? So if you look at these correlations, these are so 0.3, 0.0, 0.2, minus 0.5, 0.9, 0.7, 0.8. These are the numbers that you must have seen over here, right? So 0.3 and let me see, 1, 2, 3, 4, 5, 6 correlations, and We got 1, 2, 3, 4, 5, 6 correlations here, right? So these 6 correlations, they're rounded to 1 decimal place, so they look slightly different. But what you're seeing in this output in the linear mixed model, this part here, what you're seeing here, oh sorry, I wanted to highlight just this part here, okay? What you're seeing here is the lower diagonal of something called a correlation matrix. You're seeing this lower diagonal here, right? This lower diagonal here. So it should be 0.3, 0.2 minus 0.5 should be the first column. 0.3, 0.2 minus 0.5. You see, that's the first column. Then the second column will be 0.9 and 0.7, 0.9 and 0.7, and the last column will be 0.8, right? And there it is, 0.8, right? So this lower diagonal is what is being represented in the output of the linear mixed model random effects here, okay? And so we've extracted that as a matrix, okay? So this thing is now something called a correlation matrix. If you look at it, right, it's completely symmetric. Along the diagonals it's got ones, and on the off diagonals it's got the exact mirror image of each of those numbers, right? Alright, so what I'm going to do now is I'm going to choose some intermediate values for these correlations, because these correlations are obviously causing some singularity, okay? So I create a new correlation matrix. If you look here, I've created a correlation matrix with 0.5 everywhere, okay? The way I did that was I first created something called a diagonal matrix, which only contains zeros, and then I created another matrix that repeats 1 16 times, and it's a 4 by 4 matrix. You see that? It has 4 columns, so it's a 4 by 4 matrix with ones everywhere, and then I divide that by 2 so that everything becomes halved, right? Oops, sorry, what did I do? Right, so if I were to, let me just do this, okay? So if I were to halve, first of all, let me just generate this matrix. Right, this matrix contains ones everywhere. If I divide by 2, I get a half everywhere. But if I add a diagonal matrix, so a matrix which has ones on the diagonal, sorry, let me not do this here. So if I add a matrix that has ones on the diagonals, or let me try this before doing this, right? So let's try, if I add to this matrix a diagonal matrix, if I add this matrix to the previous matrix, look at what I get, okay? So I'm going to add a diagonal matrix. Oh God, what is going on? I'm getting tired now. Yeah. Alright, so what's going to happen is I'm going to get 2's along the diagonal because I added 1's along the diagonal here. And if I take this entire term and divide it by 2, what happens is I get 1's along the diagonal and 0.5 along the off diagonals, and which is what I wanted. I want a correlation matrix which always has 1's in the diagonals, and then I'm just putting some intermediate values for the correlations everywhere, okay? So that's how I got past the problem that my variance covariance matrix was singular. This problem I have to circumvent in order to generate new data, right? I can't generate data with a singular matrix. Okay, so now we get to the point that I have a vector of the standard deviations, you know, those 4 standard deviations for the random effects, these guys here. And I have a correlation matrix, okay, which I just created. I created this correlation matrix. Now it turns out that if you know the standard deviation, and if you know this vector of standard deviations of a covariance matrix, and if you know the correlation matrix, you can multiply these guys together to get the variance covariance matrix. So there's a built-in function in R in this SIN package, SIN package, that takes the standard deviations, takes the correlation matrix, and converts it into a covariance matrix. Okay, so this is what I've done here. I've given this vector of standard deviations and the correlation matrix here, and when I run this command, what I get, lo and behold, is a variance covariance matrix that represents the subject random effects. Okay, so I have managed to now produce a variance covariance matrix, even though I had some problems. Possibly I had some problems in the correlation matrix. I chose some intermediate values and I produced the covariance matrix for subjects, and I'm going to do the same thing for items now. Okay, I take the items random effects, right? So that's these numbers here. I take the same correlation matrix just because it's an intermediate set of values. It's a reasonable starting point. And I produce the variance covariance matrix for the items as well. So these are the pieces of information that will go into simulating the data now in a 2x2 design with a Latinsquare design. Okay. Okay, so the next step that we will take in our preparation for simulation is to first check that our code actually works, right? So one problem that we are going to face is that the function that I had defined for generating simulated data is not exactly correct anymore. The reason is that the conditions in this Levy and Keller design have codings that are different from the C1, C2, C3 contrasts that I defined. Remember that I set up the first factor levels as A, B, so that matches with what I had done. But the second, in the second factor levels, what did I have? Let's go back and see. It wasn't B, D, right? What I had was, let me see. I had A and C as the second factors level, the first level of the second factor, right? But in the Levy and Keller data, it turns out that we have different values. We have B, D, right? So we're going to have to rewrite the the simulation code such that we have to make one small change, and the small change is here, right? So we're going to change the contrast codings. There's going to be AB, BD, and BC, just like Levy and Keller had it. AB, BD, and BC. Okay, so I've changed the simulation code now to reflect the Levy and Keller contrast coding. Okay, so that's a very important change. If I'd used the original contrast coding, I would have messed up everything. Okay, all right. So then let's generate the random effects for the subjects and for the items. I've already explained that. Generate the simulated data and produce the simulated data frame. Now we can just test this code first, right? So we've set up everything. These estimates I just showed you how I computed. I've taken the number of items and the number of subjects from the Levy and Keller data, right? And I'm going to now generate some simulated data to see if it has the expected properties. Is it actually a Latinsquare or not? I must check that, right? So first of all, I expect, if it's a Latinsquare, that every subject will see exactly one item. And that's true. You can see that here, right? Every subject is seeing exactly one item. I also expect that there will be 6 data points per condition for each subject. Why? Because 6 4s are 24, right? And there are 24 items, right? So there are 6 per condition. That's true also. Then I'm checking the contrast coding, and this all checks out, so everything's correct, right? So then I'm ready now to compute power. Now what I'm going to do is I'm going to remember that I calculated that there is some uncertainty about our effect estimate, right, on the log millisecond scale. I'm going to use the lower and upper bound and the mean estimate from the data to compute my power, right? So what were the three values that I had? The lower bound was 0.03, the upper bound of the estimate for the dative effect was 0.27, and the mean was 0.15, okay, on the log millisecond scale. So what I'm going to do is I'm going to run a simulation 3 times. Okay, so basically there are 2 for loops, and what I'm going to do is I'm going to run 100 simulations, setting first setting the B1 estimate, so the first slope, to be 0.03. Then I'm going to run 100 simulations with the slope set at 0.15, and then another 100 simulations with the slope set at 0.27. So what I get is 3 sets of 100 simulations which I run with different estimates of the effect size. So this gives me a sense of how much my power will differ depending on the magnitude of my effect size. Okay, if I had enough time, what I would actually do is I would run maybe 100 different estimates, you know, taken from my guess about what possible values the estimates can have, and run lots and lots of simulations. But we don't have that kind of time, so we're just going to take 3 plausible values of the effect size just to illustrate the principle, and run 100 simulations each time. So how do I do this? What I'm going to do is I'm going to save the t-value for the dative effect. After I've simulated some data, I'm going to run the linear mix model, compute the t-value for the dative effect on the simulated data, and save it in this vector which I'm going to create in advance. Okay, so because I have three effect sizes that I'm going to look at, I'm going to create a matrix of t-values. So the t-values there'll be 3 columns representing each of the 3 effect sizes, and I'm just going to save the t-values for the first estimate, for the estimate 0.03. I'm going to run 100 simulations and save the 100 t-values in the first column. For the second effect size, I'm going to run 100 simulations for 0.15 and save that in the second column, and then so on for the third column, right? So that's what I've done for the dative, and I also saved these, although I'm not going to use these in this simulation. I just did that in case you want to play around, you know, with the other factors. I'm also going to create a matrix called failed, in which I'm going to store the cases where I fail to converge in the simulated data, right? When I run a linear mix model, if I fail to converge, I will store a 1, the value 1 there, and if I succeed in fitting the model, I will leave it as a 0. Okay, so I will just show you what these things look like. I'll just show you in a moment. Oh, let me just do that right now. So let's take a look at this new function here. We're going to test it out. This should work. Yep. And this was the test. So here, what I want to show you is that how I will simulate now. I've set this seed so that whenever I run this simulation repeatedly, I will get exactly the same results each time. That's the reason I've set a seed there. I don't want it to vary each time a little bit. Okay, so here are my 3 values for the estimates, right? 3 possible values, plausible values, and now I'm going to create a store for the t-values, and the store looks like this. It contains it contains 100 rows, 100 columns for the 100 simulations, and 3 rows. So I'm sorry, I flipped that in my head and I reversed the order in which it's stored. So basically, this first row will represent all the t-values for this first number here, and then the second row will represent this one, and the third row will represent this one. I also create this failed matrix here. This failed matrix you can look at as the same structure. This matrix will be populated with a 1. It will contain a 1 whenever there's a convergence failure in a simulated model fit. Okay, so let's look at the code. So I'm going to run an outer for loop that cycles through the different beta 1 values, these 3 values. Okay, and then I'm going to run for each of these each of these beta values, right, beta 1 values, I'm going to run a simulation of 100 times. The first thing I will do is I will take the first value, the jth value, right? So it says here j going from 1 to the length of the vector beta 1 estimate, which this length of this vector will be 3, right? So j can have values going from 1 to 3. That means when j is equal to 1, this will contain the first value in this vector here, and that is plugged into the beta 2 elements. Remember what beta is? Beta is a 4-element vector. So I'm going to replace this estimated value with the lower bound that I just estimated for this effect, okay, and calculate power for that, right? So I've put in this lower bound here in the when j is equal to 1, and then I do my I simulate my data. Once I've simulated the data, I'm going to run a linear mixed model, right, with no correlations, because I want to minimize my convergence problems on log reading time. And then what I do is, if I get a message that says we failed to converge, so that's what I'm looking for here. This says if you see anything that says fail to converge, right, in the messages, then what you do is go to the jth row and the ith column of the failed matrix. Remember the failed matrix, this one here. And so if you're in the first, if j is equal to 1 and I is equal to 1, then you're in this cell here. Put in a 1 there. That means that 1 represents that you failed to converge, right? Otherwise, if you didn't fail to converge, if you did not have a convergence failure, then save the t values for the dative effect, for the adjunct effect, and for the interaction, okay, in the 3 things here. And so you keep running this loop, and after the loop finishes, you can look at the proportion of failures. So right now we have zeros because I just initialized it, but in the code you will see, I don't know if it printed out. Oh, somehow it didn't print out the values here. But if you run this code yourself, you will see that there will be a few failures, and you can see that it's not dramatic. It's not too bad. Okay. All right. So now we're coming to the interesting point, which is that once we've done all these calculations, what we now have is 3 power calculations, one for each of the values of this beta 1 parameter estimate, right? I've run 100 simulations with this value, 100 with this value, and 100 with this value. So what we do is we look at the t values for the dative factor, and we check the proportion of t values for each of those beta 1 estimates that is greater than 2, and that we store that in a vector called power. And if you look here, what you see is something very interesting, that when the lower bound of, if the lower bound estimate of the effect were the true value, then power would be about 7%, which is really bad. If the true value were the estimated value that we have from the data set, right, then power would be about 65%, which is still below what we need of 80%, right? But if the true value of the effect were as large as the upper bound of the estimate, which is like 147 milliseconds or something on the millisecond scale, then we have almost 100% power. Okay, so what this is telling us is that we have a lot of uncertainty in our estimate about the power, right? We can't be very sure what the power is given the effect size estimates we are working with here. Okay. I want to remind you here that power is a function of 3 things. Power depends on the effect size, on the standard deviation, and in the linear mixed model, all the variance components, right? Not just the standard deviation. And the sample size, that is the number of subjects and items, right? Often in papers, you will see people writing, oh, power in our experiment was 80%, right? We set up our experiment to have power 80%. power is not a number. Power is a function, and it should always be represented as a function of these variables. Okay. We will do some homework exercises where I will ask you to compute power as a function of sample size. Okay, so you will see that later. So what I did here was I gave you a simple range of power estimates for different effect sizes, right? So you could now generalize this code for a range of effect sizes, or plausible effect sizes. You could compute compute power, right? And that's what you should do when you're studying your power properties of your design. Okay, so having shown you all this, now what is all this good for? Why am I making you sweat so much and think so much about power? What I'm teaching you here gives you tremendous capability for understanding the properties of your design that you're working on, right? More concretely, when you're working on a particular experiment design, you can use your existing estimates to figure out how many subjects you're going to need to achieve 80% power. This is a very common problem that we face and we often don't know how to solve. This method that I've shown you allows you to leverage the data you have to work out how much data you're going to need to be able to make sensible inferences, right? One other interesting thing you can do with this kind of simulation is to study the type 1 error properties of your model. This will be a homework assignment. Okay, so I will come back to this point. That's it.